So suppose this were a classical program. What did we do? Well, we computed something in the first register. We did something and we computed something in the, well, we computed something in the second register. We did something and we got a different value in the first register. Then we measure the first register and we throw the second register away. So if we throw the second register away, because the only information we care about is y. We don't actually care what f of x is. And in fact, f of x is equally likely to be all possible f of x's because the probability of seeing y, f of x, only depends on y, which means f of x tells us no information about anything because all values of f of x are equally likely. So you classically, if you ran this through an optimizing compiler, we'll say, well, we compute f of x. We never use it. Why bother? Let's see. Y. Yeah, we computed f of x. And we computed this y only from this x. So why bother computing f of x? So this is what an optimizing compiler would do for a classical program. But now, if you erase f of x, there's no information about f anywhere, so this program can't possibly work. So the reason this works is the back action from f of x to x when you computed f of x, which is, I don't know, I think it's very non-intuitive when you first look at this kind of stuff. Because everything in quantum mechanics, if system A affects system B, then system B affects system A. And if system A affects system B in some basis, system B affects system A in the conjugate basis. So this is, so if you have optimizing compilers for quantum computers, they're going to have to behave differently than ones for classical computers. So you can't do this. OK, so this is what we get. We get a y such that y is perpendicular to c. And we get a random y that is perpendicular to c since all possible y's have equal probability. Good?